Hi, here comes a purely analytic statement about approximating continuous functions with polynomials. However, the proof is incredibly nice and is probabilistic using the weak law of large numbers. The theorem itself has no probability in it. It's an analysis theorem. It says the following: let f be a function from the closed interval 0, 1 to r. And I also assume it's a continuous function. Continuous function. So given is a 0, 1 to r continuous real function. Then it can be approximated by a polynomial. So to be more precise, for every positive epsilon, there exists a finite integer n and a polynomial Bn of x of degree n such that the polynomial and the function are uniformly close, closer than epsilon. So what do I mean by that? If you take the supremum of the difference between the function and the polynomial, the supremum for all x's in the 0, 1 interval, so take the sup of the difference, this is going to be smaller than the given epsilon. So this supremum can be made arbitrarily small by going far enough in n, taking a large enough degree polynomial. Okay? And there is nothing probability in this statement. However, the proof is going to be probabilistic, and it's going to use the law of large numbers. So fix x in 0, 1, okay, and let a random variable big X, so this is my capital X, this is my small x, be binomial of parameters n and this x. Notice that x is between 0 and 1, so it's a probability. And I can plug it in as the probability parameter of binomial. Define the Bernstein polynomial. Define the Bernstein polynomial this is going to be my polynomial Bn as simply the expectation of f of x over n. Okay, x is my binomial. X over n is a random variable between 0 and 1. I take the function of that, the function f of that, and this is random at this point, so I take an expectation on it. This expectation is absolutely fine because continuous functions are measurable and it must be bounded, so it's all fine. Okay, so what is this, if I want to write this out a little bit, what is this polynomial? So this is the sum from 0 to n for all possible values of my binomial random variable. Maybe x equals to I, in which case I have f of I over n, and then I need to have the probability that the binomial is I, which is n choose I, x to the I, and 1 minus x to the n minus I. That's just the binomial mass function of parameter n and x at I. And of course, it's clear to see that each term here is degree n, because it's 1 minus it's x to the at most n minus I power multiplied by x to the I. So actually, this product will have terms from from I to n power. If I add all these up, this is a polynomial of degree n. So that's going to be a Bernstein polynomial. And what I'm going to show now is that this polynomial approximates my function f in this sense, in a good way. Okay? Now, to show that, let's notice the following fact from analysis. Actually, it's called Heine's theorem. Heine's theorem tells us that we have a closed bounded interval here. Any continuous function on there is also going to be uniformly continuous. So f is also uniformly continuous Okay, so Heine's theorem again tells me that any continuous function on a compact interval, a bounded closed interval in the real numbers, is also going to be uniformly continuous. What does it mean to be uniformly continuous? It means the following. If I fix epsilon, then there is going to be a positive delta, so that f of x minus f of y in mod is smaller than, I could use epsilon, but for my purposes I'm going to use epsilon half, doesn't matter, whenever x is between 0 and 1, x and y are both between 0 and 1, and they are closer to each other than delta. Okay, so that's uniform continuity. Continuity would mean that for every epsilon and every x there is a delta, so that fx minus fy is closer than that, when x minus y is closer, smaller than delta. Uniformly continuous means that I'm allowed to move with x wherever I want. No matter where I pick x, this continuity will still hold around that x. Okay, so that's uniformly continuous. X is not fixed, x and y are both moving on the interval 0, 1. They just have to be closer than delta to each other, and that will make my function increment smaller than whatever I want, in this case epsilon half. Alright, so then let's start an estimate of fx minus bnx. So let's start to write up the difference between f and b. What is this? So this is the, b is by definition the expectation of my function at x over n. All this on the in the mod. So this is I can actually so x is random. Expectation is according to the binomial distribution of x. Little x is not random, so I can move little x in and out the expectation. So I'm going to move f of little x inside the expectation. And now you probably start to develop a feeling for what's going on. X is binomial. X over n will be close to its mean, which is the probability parameter, which is little x. So this guy should be close to little x, and that's exactly what we're going to use. But we have to use it in a clever way. So we're going to say that there are actually two cases in the world. I can still keep this equal for now. There's a big absolute value outside, and I'm going to put here e of f of little x minus f of big X over n, and I'm going to multiply this with the indicator that x minus big X over n mod is larger than delta. Okay, I'm going to look at this expectation first, and I comment on this notation in a minute. And I'm also going to do the same with the complement event. So take this difference under the event that x minus x over n mod is smaller than equal to delta. All of that in a big absolute value. Okay, so there is a notation I have to explain here, and the notation is that the expectation of some random variable y under an event e is defined to be the expectation of this random variable times the indicator of the event e. So that's just a short notation. This thing here and also that thing there is just a short notation for expectation of the difference times the indicator that x minus x over n is larger than delta, or expectation of difference times the indicator x minus x over n is smaller than or equal to delta. Notice that these two events are complement to each other, so exactly one of them will occur, and that means that if I add these two expectations up, then the sum of these two indicators is always exactly 1. So that's why this line is equal to that line. Okay, it's called the probabilistic splitting of the expectation. We split the word according to two cases, One case when x minus x over n is larger than delta, and the other case when it's smaller than delta. Okay, the next step I want to do is, the next move is going to be a triangle inequality. I see the sum of two expectations in an absolute value. This is smaller than or equal than the sum of the absolute values. So put here the same expressions under the first indicator or first event, and I close the expectation and I close the absolute value, and I start a new absolute value, and then f of x minus f of x over n under the other indicator, the complement indicator. The difference is less than delta. Okay, and closing the absolute value. Okay, and now we're going to go back to our assumptions and see why each of these terms is small. The first term, so they are going to be small for a different reason. In the first term, I have an event that my binomial over n is far from its mean. The mean of my binomial, notice that the mean of my binomial is the product of the probability parameter x and n. So the mean of x over n is x, and according to the weak law of large numbers, x over n should be close to x with high probability. So this is a small probability event. Okay? So this part is going to be small because this is a small probability event. And I'm going to show you in a second how to make use of this. So that's why it is going to be small. Now in the other event, I have an indicator that x is close to x over n, closer than delta, and that is a large probability event. But under this event, if this event happens, then I know that the difference will be small by continuity, uniform continuity of f. Okay, so this part will be small because f is uniformly continuous, and if x is closer to x over n than delta, then this will be small. Okay? If x minus x over n is larger than delta, then this indicator makes this whole business zero anyway. So those cases I don't have to consider. They are already included in the other part. Okay? So to make this precise, here is what I'm going to do. F is continuous on a closed bounded interval 0, 1. So it reaches its maximum in there, which means that the supremum of fx mod, when x is between 0 and 1, is finite. I'm going to call this m. It's finite. F cannot exceed, in fact it's a maximum because f will take its maximum somewhere. It cannot exceed some number m, which only depends on my function f. Okay? That means that the difference here in absolute value, that means that the difference of any two function values can never be larger than m for any x and y in the closed interval. It will never exceed 2m's. Okay? So I'm going to bound the first expectation, so this whole thing is then bounded by, I take the largest possible thing this difference can be. It can never ever be larger than 2m. And then I have the expectation of an indicator. An expectation of an indicator is always the probability of this event under the indicator. So I have to look at the probability of this. This is the first term is bounded by this expression. The overall possible maximum of this difference, that's 2m, times the expectation of the indicator, which becomes this probability. Okay? Now the second term is going to make use of uniform continuity. If x and y are closer to each other than delta, which is exactly what my indicator tells me, then the difference of the values of the function is smaller than epsilon half. So for the second part, the absolute value of this cannot be larger ever than epsilon half, and I could apply the expectation on this indicator, which will become the probability of this event. This is large. This is supposed to be close to 1. So I'm going to not bother with this probability. I'm just going to replace that probability by 1. I'm not losing much, and that makes the whole thing bigger. Okay? So the second term, this difference is never larger than epsilon half, and this is just a probability. If I hit this with the expectation, it's never larger than 1. So these are my terms. Okay. Now, this thing goes to 0 as n goes to infinity. In fact, I actually have an error bound on this from the proof. So the proof of the law of large numbers, I need a somewhat more precise error bound, is going to be sigma square over n, and this case delta square. So I'm actually, it's not enough, you'll see in a second why, it's not enough for me to say that it goes to 0. I actually have to add a little bit more precise information here. According to this proof we had just before, this is bounded by sigma square, okay, over n times delta square. I have delta instead of epsilon. Where sigma square is just going to be the variance of my Bernoulli. What is sigma square? Is the variance of a Bernoulli parameter x. And why is that? Because if you look at the assumption I started with, I said that let x be the binomial nx random variable in distribution is the same as the sum of, call it k, 1 to n x k random variables which are Bernoulli of parameter x each and iid. Okay, the sum of Bernoulli is binomial, and the probability parameter is x. Okay, now this is the variance I need to consider here, the variance of these iid Bernoullis in the law of large numbers. What is that? Well, look it up. Variance of the Bernoulli is x1 minus x, and here comes the point. This is uniformly bounded by one force for any x in the interval 0, 1. This is a parabola. The maximum is at x equals 1/2 when the value is 1 force. So sigma square is always bounded by one force, and that's important because I want to prove a uniform bound here, a bound that doesn't depend on x. So I have to get rid of the x dependence, and I do that by bounding uniformly by one force. So I can continue here that this is smaller than or equal for any x than 1 over 4n delta square. Okay, so it's not enough to say that this goes to 0 for every x. I need to say that this goes to 0 uniformly in x. I don't want an x dependence. So I continue here by saying that this is 2m over 4n delta square for the probability and epsilon half. Okay, and now what do I want? Well, what I want is to prove the theorem, is to prove that for every epsilon I can pick a large enough n so that this supremum is smaller than epsilon. Now, the supremum part is already okay because I'm calculating fx minus bnx, that's what I have a bound on. The supremum is okay because there is no x dependence here. So I can already, whatever I do next is already uniform in x. There is no x in here, and so the supremum is happy. Supremum in x is already fine. All my bounds are uniform in x. I don't need to bother with x anymore. But I still need to show that this can be made smaller than epsilon. So how do I do that? Step one, fix epsilon. which we already did. Okay. Step 2, for that epsilon, fix delta, which is what we do here. So fix delta for that epsilon. Okay. Step 3, fix n large enough. Fix n large enough so that 2m over 4n delta square is less than epsilon half. Once we fixed epsilon and delta, we can find n large enough for this. And in that case, when we have that, then this whole business becomes smaller than epsilon. And at this moment, we're done with the proof.